Okay, final question for chapter 3 of Introduction to Statistical Learning, question 15, parts A through D. This will be in R, and I will make another video for Python later. Here's our question, and we'll just tackle these one at a time, but we are going to be using the Boston data set, and we are going to be predicting crime based on the other variables in that data set. Okay. So we need to install the ISLR2 package. I think to this point I've just been using ISLR when I've had to install anything. But anyway, we need the second one. I thought we might need the mass package. I don't think we actually do, but I've just left it in there. Anyway, and then as part of the mass, or as part of the ISLR2 package, we have the Boston data set. And here is the Boston data set here. Okay, so we're going to be predicting this variable using all of these. Okay, with simple linear regression. We will first do this with univariate regression. So we'll have a separate regression for ZN, for industry, for, I'm not sure what that is, for Knox, for each of these. Okay. In order to do that, rather than write one line of code for each regression, I am going to use a loop here, the lapply for, well, the lapply, I think it stands for list apply to list, but anyway. So I'm going to first subset my data into the predictors. So I have my predictors, and I'm subsetting the Boston data set, and I'm removing the crime variable, right? Because it's not a predictor, it's the outcome that we're trying to predict. And so then I'm going to have all of these models, and so I'm using my loop here. So for each of the entries in predictors, for each of the predictor variables, I'm going to run a function, okay? And that function is just the LM function, right? And so I'm going to regress crime on the xth element of predictors, okay? So I'm going to run all of that, and then I'm going to just look at the coefficients from each of these regressions, right? So I'm just pulling out the summary of each of these regressions, okay? And then looking at the coefficient, and I'm not looking at the intercept, so I remove 1, okay? And then just to make it pretty, I'm using this do call method where I take the coefficients from the first regression and bind it to the second regression and bind it to the third regression, and so on and so forth. Okay, and so when I do that, this is what I get. So these are regression coefficients for the individual regressions, for the univariate regressions. Okay, however we want to look at that, there we have it. Okay, so we can interpret that however we want. Loosely speaking, we see that really the only thing that does not have a significant effect or significant association is Chaz. I'm not sure what Chaz means. And it also asks us to create some plots to back up our assertions. I'm not really sure what this is trying to refer to, but I've made a plot here. And this plot is not pretty to look at. So, but anyway, it is a little bit interesting. So along the x-axis, we have the estimate, right? We have the estimates. And then along the y-axis, we'll have the p-values, okay? With demarcations at an estimate of 0 and a p-value of 0.05. Okay, and we see that the one that is out of place here is the Chaz one, which we already saw. So I don't know if this plot really supports our assertions, but there we go. Okay. And so now we're going to do something similar, but we're going to fit a multiple regression. All right. So instead of regressing crime on each of these independently, we will throw all of these into a regression. Okay, and so I'm using the LM function again, and I'm just calling this model for all. So I'm regressing crime, and then it's being regressed on. And when I put this period on there, it just means everything else. So instead of having to detail every other predictor variable. Okay, and so then I'll get the coefficients, again removing the intercept. That will just help us later when we plot some of these things. So anyway, so now here is our coefficient table for the new for the new regression, the multiple regression, you notice that not all of the p-values are now significant. So something has changed. So I want to kind of show how they've changed in a couple of different ways. So the first way is I just have the two sets of regressions just piled on top of one another, right? So the left hand here, the left-hand columns, is the univariate and then the multivariate, right? So we can just look at one and the other, right? And just see that the estimates have changed, the p-values have changed. I can also look to see how much the estimates have changed and the p-values have changed, right? So how the difference in estimate and the difference in p-value, So all this is I subtract the univariate, or I subtract the multivariate from the univariate, okay? And I get all of these, okay? And so we can look at those. We could also plot these, and this is not the prettiest plot in the world, but partly because there's just too much going on. And I've color-coded it. I think the color coding is a bad idea here, but you could play with the code, and instead of having using marker colors, you could just turn it all to black. But I don't think this is a very useful one. But anyway, the idea here is that, again, we have the estimate and the p-values as the axes, and then each of the coefficients has both a open circle and a solid circle, and the solid circle represents the univariate regression, and the hollow circle represents the multivariate regression. And you can see how the estimates and p-values have changed. Okay, and there's lines connecting them, and anyway, this thing is a mess. But the next question will prompt us to give clearer plots. Okay, and so it just wants us to look at the estimates for univariate and multivariate, and then to plot one against the other. And I'm going to add some fancy stuff. I'm going to add some error bars in both directions, and I'm also going to make a separate plot for the p-values. Okay, so again, color coding might be a bad idea here, but anyway, but when we want to compare the coefficients to the p-values, something like color coding might be a good idea. But here we have the coefficients. So again, on the x-axis we have the univariate, and then we have the multivariate. All right. And so here's a data point that just kind of stands out here. And so we get the error bars in the univariate as well as the multivariate, okay? And then we also have the same for the p-values. So the p-values along the univariate and then the multivariate, and just kind of what we saw is that with the multivariate, so in the univariate, most of the p-values were stacked up around 0 with one exception. And then with the multivariate, it becomes quite dispersed. Okay. Again, here's the code for all of that. I won't walk through the code, but you can go to the Colab sheet and look at it. Okay, now finally, it wants to know if there's evidence of nonlinear associations between our predictor variables and our outcome variable. And it suggests that we do that by running a polynomial regression up to the 3rd degree here for each of these. Okay, now the problem is that we can't do each of these because in particular, one of these values, Chaz, the problem child, it must be a categorical variable because it does not have 3 unique values. Okay, so in order to run a regression like this, you need at least as many unique data points as there are terms in the regression. Okay, and Chaz doesn't have that. So we have to omit Chaz from this. Okay, so I have to create a new set of variables. Okay, so I'm calling it no Chaz, which is just predictors from part A minus Chaz. And then I'm just rerunning the code from A, but now my linear model is no longer just regressed on each predictor variable. It's regressed on a polynomial for the to the 3rd degree. Okay, so when I run this, I get this view right here. So we have Zn. 1st degree, 2nd degree, 3rd degree. I'm sorry, I didn't make that nicer. Industry, 1st degree, 2nd degree, 3rd degree, so on and so forth. And so it asks us, is there any evidence of nonlinear associations between any of these things? Well, insofar as we trust our univariate analyses, well, then all we have to do is go p-hunting here and look for significant values that are either in the 2nd or 3rd slot. So anyway, so we see that, yeah, quite a few of these predictor variables do seem to have some kind of nonlinear relationship, or there's evidence of a nonlinear relationship with crime. Okay, so we are done with chapter 3, and that is relief, and we will be moving on to chapter 4 next time. Thank you.